Okay, so welcome everybody to this beautiful place. We are fortunate to have today Dmitry Green as a speaker. Dmitry received his PhD in condensed matter theory from Yale in 2001, where he worked on Majorana fermions and strongly correlated systems. Together with Nick Reed, he co-authored a seminal paper on non-abelian quantum Hall states, which is basically the intellectual foundation behind topological quantum computing. He was the recipient of the National Science Foundation Fellowship, Yale Gibbs, and the Winston Churchill Foundation Fellowships, where he currently serves as a trustee. Dmitry has continued to publish original research after moving into the business world, in particular McKinsey Consulting and the asset management industry, where he has had a successful and distinguished career. This is perhaps the most amazing thing, is that he maintained kind of two career paths, both successful. And now he's actively pursuing implementations of his ideas on quantum computing, and is very interested in commercialization of quantum technologies in general. He's based in New York City, and today he's going to talk about his recent work, which I think is about to be published in PRL, if I'm correct, on related topics. So welcome, Dmitry.
All right, thank you very much for that very nice introduction, Victor, and thanks to everyone for coming and attending this seminar. So I think what's fun for me is to talk about some of these ideas, and we're going to be talking about a lot of topological things and quantum computing and so forth. Now, as I understand it, the audience has mixed specialties, so I'm going to try to mix it up a little bit, and I'm going to try to start very, very broad and a lot of conceptual things, and just only get to the math by the end, and sprinkle some math throughout. One thing before we jump in, so the talk is basically there's two components to it. Yes, the first piece is going to be published in PRL, and there's another paper that Claudio Shimon and I just posted on Archive, which is going to be kind of the punchline of the talk, the superconducting, regarding superconducting circuits. So just to jump in, the broad goal really is to build topological phases in engineered structures. And the real constraint is with available interactions. The applications of this, and I'm not going to spend too much time on the actual applications, people have probably read about a whole bunch of them: topological qubits, error correction, quantum memory. I'm not going to spend too much time on the specifics of that. Here, this is really a conceptual kind of framework that we want to lay out here. And the real crux of it in the framework, and I'm going to keep using this word over and over, is combinatorial gauge symmetry. And it's really a mathematical structure that we kind of, I don't know what the right word is, uncovered or imposed or found, that really makes this available interactions piece possible. And so before we jump in, I just want to say one thing about the business world. It really imposes a very strict discipline on you of practicality. And I don't just mean something that could be built, for example, but even in thinking, it was actually, that discipline was very helpful here from the mathematical point of view, because when you're trying to solve, the problem is constrained, as you'll see. We were trying to come up with some sort of topological phases only with what's available, right? So only with interactions that can be built in the lab today, not with putting in like 12-body interactions or some other clever things that are, for those of you who are familiar with all these exotic models are in there. So there's going to be basically three pieces in the talk. I'm going to talk about the motivation, and that's going to be at a high level. I think it's important to go through it. Then I'll talk about topological phases, and I'll try to make that broad as to what they are, why they're interesting. And I'll get to our proposal, which will discuss a lot of the combinatorial gauge symmetry, and then finally, how to actually potentially build it. So motivation. I assume that most people in the audience have probably read about the quantum computing, the state of quantum computing, and the various approaches, at least at a high level. There's really, in my mind, there's three big buckets of ways that people are trying to get at it. One is the quantum gate array. There's also quantum annealers, or really there's only one commercially available right now, well, one today. And finally, there's topological quantum computing, which is only one major company is pursuing that right now. So quantum gate array. This is my one-page overview of quantum gate arrays. And that's all I'm going to say about quantum gate arrays for the most part. You have a set of qubits, and there's a bunch of unitary operations on those fixed qubits. This is the probably, I'm not sure if I want to say conventional, but seems to be the most popular approach today. IBM, Google, Intel, Rigetti, many more are pursuing this type of approach. The maximum number of qubits, depending on the machine and the implementation today, is around 50 to 70. And as you probably know, you need several orders of magnitude more to build an ideal quantum computer. Quantum annealers is the other approach. There's only one company, as far as I know, pursuing this right now. That's D-Wave. They've been at this for a while. And this is an interesting approach because it's very, very limited qubits functionality. You have, just to get into the technicalities a little bit, you just have one type of interaction, which is a ZZ interaction. And then you have a transverse field. And the idea here is that you map some sort of problem, or at least the motivation for building this. It's not the only use for it, it turns out, as we will discuss here. But the original motivation is to solve these kinds of problems where you map some sort of problem into a surface where the minima are supposed to give you the solution. The minima are in the space of these binary variables, z, sigma z, on different sites, which are +1 or -1. And then you put quantum fluctuations in there, which make you bounce around in this space of minima, and then hopefully settle into quench into some sort of some good solution. The maximum number of qubits here. So now this is a very limited set of interactions. You don't have all of your universal gates, et cetera, et cetera. But the maximum number of qubits here is 2,000. And I think today, D-Wave, roughly 2,000. And I think D-Wave is supposed to come out with another machine, which will have about 5,000 qubits. So the idea here is that you have many, many qubits. They're very limited, but they're mass fabricated. And I will come back to this because this was a big motivation for us to attack the topology. So most of the—
Dmitry, I have a question. May I ask a question to Shankar? So for the annealer, is there any quantum error correction theorem? I mean, you are putting them on the same footing. So I'm asking, annealer is more like an analog machine, right? There is no quantum error correction theorem for annealing, right?
I think there are ways to implement it with a gazillion qubits, but let me just table the error correction for now. We can come back to it later.
All right.
But the quantum piece, you're right, there is just the classical piece is the ZZ interaction. You can view it classically in the Z basis. And then the sigma X is the quantum piece that obviously doesn't commute with the Z's and makes them fluctuate. So most of the qubits, before we talk about topological, are based on something called the Josephson junction. For those of you not familiar with it, this was discovered or proposed by Josephson back in '62, for which he later got the Nobel Prize. And the basic idea here is you have two superconductors. There's an insulator between them, and the current tunnels through the insulator. And it's a superconducting current. And for those of you familiar with superconductors, one of the ways to characterize them or describe them is by a phase. So each superconductor has a phase, phi1 and phi2, and it turns out that the current is proportional to the sine of the phase difference, and then the energy, or Hamiltonian, is the cosine of the phase difference. So this is really all you need to know about Josephson junctions for this talk, but I wanted to highlight this because it's at the heart of most of the superconducting approaches today in D-Wave and Google and IBM. They're one way, shape, or form, they're based on this phenomenon. Okay, so now the third piece is the topological quantum computing. This is a very, talking about error correction, this is self-correcting, if you will, because the idea here is that you create kind of entanglement or topological entanglement throughout the whole system. And the qubits kind of stabilize each other. There's coherence, or quote unquote topological order, to be precise, across many, many, many qubits. But it's very difficult to do. You can compute with it if you get these quasi-particles in there, or excitations called anyons. And you would have to physically somehow drag them around adiabatically. And that's what gives you this computing power, and the stability in the error correction comes from the topological order. But depending who you talk to, there's either 0 qubits that have been seen or 1 on that order. It's very difficult. Major player is Microsoft, who've chosen that path. And as Victor mentioned, that's something that I worked on. I did not work on the topological computing piece of it, but Nick Reed and I were working simply on the physical phenomena of the Majorana fermions, which turn out to be the anyons in this case. Okay, so the question that here's the core of the motivation. The question that we were attacking is the following. You've got these two pieces. You've got on the one end of the spectrum, you've got D-wave, for example, with lots of qubits, but they're very limited. Then on the other end, you've got this very powerful topological system, but it's theoretical. It's very difficult to build. So can we actually build topological qubits by rethinking the geometry and connectivity of the conventional qubits? And by conventional qubits, I mean all of those different flavors of qubits that are made out of the Josephson junctions today. So can we somehow put those together, glue them, connect them, arrange them? Can you do anything to build some sort of topological state, any sort of topological state? And it turns out, and that's a mathematical problem. And it turns out that, what you have to do for it is what we're calling combinatorial gauge symmetry. That's the mathematical structure that will underlie this. It's relatively simple once you see it. I'm sure to show you some pictures. And the interesting part about it is that you can do it, theoretically at least, even just in a quantum annealer type device. So just going back to this picture, so even with the simple Hamiltonian of ZZ interaction and the sigma and one single transverse field and everything, you can create topological states in principle. And that's the core of the idea. And then I will show you a couple different ways that you can implement it and talk about what we're working on. So along the way, I think what we're gonna have to do is we have to describe what a quantum spin liquid is, or I'm not gonna spend too much time on the specifics of what it is, but really along the way to addressing this, we're attacking an old problem that has been around in one way, shape, or form. People have been thinking about it since the 70s in quantum spin liquids. So it was introduced in the context of particle theory as a toy model called Z2 gauge theory. It was then picked up by Anderson a little bit later in trying to explain superconductivity, some superconducting materials in the early 70s. Phil Anderson, as you know, was a key condensed matter theorist. And ultimately, it's really underlies the modern understanding of topological order and anyons and fractional statistics and everything else you hear about when you read about topological computing. So, and there's a zoo of different results around it, very, very rich theoretical results. The challenge is that there has been no experimental realization of these systems. The one thing I do want to point out that in parentheses, I put gapped here, and that's important because some gapless quantum spin liquids have been found and observed, like you can read about quantum spin ice or spin ice. But what we need is a gapped quantum spin liquid. So that if you want to compute anything, you need to have an underlying manifold that's not, quote unquote, polluted by the excitations. So the best way to illustrate this, I think, is with an example of a quantum spin liquid. And the best known example, probably in the context of quantum computing, is the Toric code introduced by Kitaev. And the core of the system is that you have quantum spins on a lattice. So you have a lattice here, and the spins, these are just spin 1/2, let's say, and they live on the links, in the middle of the links. So Z is in that basis of Z, you just have up, they're either up or down, and X will flip them. The sigma X flips them. So the key to this model is, and the key to a lot of what we're doing here, is a 4-spin interaction, where the energy is simply the product of 4 binary variables. That's the basic interaction. And the sigma Z's could be +1 or -1. And it's a 4-body interaction, so you can imagine it's very difficult to find a clean system. In fact, nobody's found one like this in nature or constructed one, but that's what makes this model work. And the way it makes it work is you get you look at a star. So this is each vertex, and around each vertex you have spins. Let's color each spin. If it's up, color it blue. If it's down, color it minus, or red, -1. And you have 8 possible configurations here. You see the product of 4 binary variables here is always +1 if you have an even number of up or down. And these all have to be degenerate, and that's the key. because then what happens is you have these incredible loop gases where the ground state is really a macroscopic degeneracy of all these configurations. See, I drew a sample one here where every star is happy, but because every star has 2 legs or an even number of legs that are red and an even number of legs that are blue. So at each star, you have the same quote unquote parity. Now you could do what's called loop surgery. And you see what you do is you can just flip all the stars around a single square, around what's called a plaquette. And I still get a happy state, right? And I can keep doing this, and I can have infinitely many of these happy states. And the ground state is going to be a superposition of all of these types of loops. So the plaquette that makes it flip is going to be the product of sigma x around the plaquette. So never mind the mathematical form, we'll come back to it. But just remember that it's a plaquette operator. It's a little bit like Stokes' theorem in calculus, right? You're just flipping all the legs around a plaquette, and it doesn't change the ground state's energy because all of these states are still happy. All of the stars are still happy. And that's what's called gauge symmetry. I could just change one plaquette, and locally, I don't have to touch anywhere else in the system, and I still get a ground state. So now what happens if you do break this law? You can break a bond. If I break one bond, and I always have to, what you notice here is I always have to make 2 stars unhappy. I can't just make 1 star unhappy, because if I break 1 star, I have to break one next to it. Now you see I have those 2 stars with the X's next to them. I only have 1 red leg coming out, an odd number of legs. But now what I can do is I can move this excitation along. I can fix 1 star and break the next star. So I still have 2 excitations, and I can keep moving them along. So that's what's called, that's really at the heart of this phenomenon of fractionalized charge, right? I've created 1 excitation, and then I start moving it around, start breaking it and moving part of it around. Okay, so every time I do this, I create a trail of happy stars, and I only have 2 broken stars. And I can keep doing that, but now look what happens when I come back. I just fixed the whole loop, and now the excitation is gone, right? But I've still done something, right? I've still gone around the loop. And this loop, in fact, can be contracted to 0 if I'm sitting here on the plane. So I create all these plaquette operators, and just like in Stokes' theorem, I could just collapse this whole loop down to nothing, and the excitation is gone. Unless, let's say I put a hole in the lattice. Now I can't contract the loop anymore. Okay, so that's really what gives you the topology. That's at the heart of all of these topological models, is I have some sort of long range excitation, if you will, or deformation, and I have some sort of underlying topology, in this case a hole, inside in the underlying lattice, and I can't contract this hole. And so that's what gives you this kind of topological entanglement over many qubits, right? Each of these stars can be thought of as an individual qubit, and stability. And you could store quantum information this way. You can design quantum memory this way. So this is really the mathematical concept underlying these kinds of topological states. So, okay, now let's move on to the problems. It's a very nice picture, but there's 2 problems with it. One is, as I alluded to before, 4-body interactions have not been found in nature or engineered in nature yet. And quantum spin liquids, you need usually a 4-body, all the ones that I know need 4-body or more interactions. There are some very exotic models with 12, 24-body interactions, very complicated. The only 2-body example that I know of is this Kitaev, a honeycomb model, but there you need an XX, YY, and ZZ interactions separately. This interaction has also never been engineered or observed. So there's a problem of implementation here, as nice as this topology is and as beautiful as it is, and as much as we'd like to have it for the stability. The second problem is, of course, people have recognized this kind of challenges, and they tried to solve it before with, usually this approach has been known as ancilla spins or gadgets. And with 0 transverse field, you can indeed get this kind of degeneracy of 8 stars. Remember, all those loops are only possible if you have the degeneracy between all these 8 stars, because I can make all the stars happy by going through the system. However, if you introduce a transverse field, this degeneracy breaks in all of those ancilla approaches or gadgets. So now you don't have any more of this loop gas. And in fact, in the language of condensed matter theory, you get in most of those systems, you'll get what's called order by disorder, and your ground states become, they crystallize, and you don't get these kinds of topological orders extended over the whole system. So that's problem number 2. So problem number 1 is the practicality of actually seeing this. And as physicists, that's a big problem for us. And problem number 2 is we need this degeneracy. So solution. So this is now we're going to get to how the combinatorial gauge symmetry works. And I'm just going to do some pictures in steps. So the question you need to ask, and it turns out that the core question underneath this concept is, what symmetries will preserve the commutation relations for n spins? And because at the heart of it, if you have spin 1/2 objects and you're trying to have some sort of symmetry, whether it's some sort of gauge symmetry, you need, whatever you do, you need to preserve the underlying quantum mechanics of the spins. So for example, so let's look at fermions, for example. If you take 2 fermions, it's well known. You could take bosons too. You could take unitary combinations, or crudely speaking, linear combinations of fermions. And you could, and in this case, I just took a basic one of plus minus 2 fermions. And all the anti-commutation relations in this case are preserved. For fermions, of course, it's anti-commutators. For bosons, commutators. For spins is different. Spins are not fermions or bosons. The commutation relation, they have both commutators and anti-commutators. And in fact, if you try to do this for spins, you have a problem. You can't just take linear superpositions of different spins. You can check. You don't need to check this. It's kind of it's a trivial exercise. But you will break the commutation anti-commutation relations if you take linear superpositions of different spins. So how do you fix it? Or let's ask the question differently. And instead of, let's not fix it, but let's say which transformations are allowed. So in general, you can hit these spins with unitary operators. And as the quantum mechanics, those of you who had quantum mechanics in college, you'll know that it's called an SU2 symmetry. It basically rotates the spins. So let's see if my cartoons in Keynote work here. Yeah, so you can rotate the spins individually, and you'll still preserve all the commutators between the spins. Or you can actually permute them. Okay? So it's kind of a trivial observation when you look at that picture. But when you translate it into what's going on at the level of the states, you can characterize it as what are called monomial transformations. So now in this case, we have 4 spins, sigma 1 through sigma 4, and each one has 3 components, x, y, and z. And the permutation and rotations can be encapsulated in what's called a monomial matrix. And the monomial matrix has a non-zero element, only one non-zero element in each row and column. And each element has to, in this case, if you're going to transform these spins, each of these elements has to belong to a rotation group, right? You're rotating each of the spins and you're permuting them. So in general, this kind of transformations will preserve your underlying quantum mechanics or commutators, anti-commutators of the spins. So just to continue on with the math a little bit, for those of you who are more mathematical, you can write this monomial transformation as the product of a rotation and a permutation. So individual rotations and permutations of the spins, and it's known as a semi-direct product. It's not a direct product. And further, if you dive a little bit deeper, mathematicians call this thing a Reith product, a specific example of a Reith product. So here's a nice little, here's a shoe example. So I find this a useful way to picture what's going on here. So let's say you have a problem where you start with 4 pairs of shoes here. And what you need to do is you need to give everybody give everybody a pair. So you want everybody shuffle the pairs around, want everybody to get a pair, but you don't care what order they get the left and right in. So you can switch the pairs, and then you can permute them. And then every person's still guaranteed to get 2 shoes and they'll be happy, right? They can figure out which foot to put it on. So it's kind of an analog of the spin flip and permutation. So that's the underlying mathematical structure. So now, how do we actually use this to get a gauge symmetry? So this is, I'm going to talk about 2 pieces here. First, I'm going to talk about the spin systems, and that's the paper that Victor mentioned that just came out in PRL with Claudio and Z Chang, who is at Maryland right now. We have that out in PRL, and in spin systems, I think it's an intuitive place to start. And then after we get through that, I'll talk about how you actually build it with superconducting wires, which is the subject of our recent archive with Claudio. So in spin systems, here's how we can use that underlying monomial symmetry. When you dress up the lattice. So what you see here is the original lattice of the Kitaev Toric code, right? Where you have the spins, the green spins are the ones on the links. But now we introduce what we're going to call matter spins inside each vertex. Those are the 4 blue spins inside each vertex. And the green spins we're going to call the gauge spins. So notice that the matter spins don't talk to any other matter spins. They only talk to the gauge spins that are around them. And the gauge spins are shared. Okay, so we're going to call them mu and sigma. And now we're going to put an interaction between them. And this is the second piece of the puzzle. We're going to put an interaction between 4x4 interaction at each vertex. We're going to connect every sigma, every gauge spin to every matter spin inside the vertex with either a ferromagnetic or antiferromagnetic coupling of the same magnitude. So I illustrated here in red lines the connection between 1 gauge spin and 4 of the mu spins, matter spins. I didn't draw the other connections between sigma 2, sigma 3, and sigma 4 to these mu's. That'll just make it too crowded. The dotted line is a -1, and the solid lines are a +1 sign of the interaction. Call that J. So the Hamiltonian of this thing is now going to be written as sigma z times mu z, and the matrix that connects them is a 4x4 matrix that encapsulates this ferromagnetic antiferromagnetic coupling. Turns out this thing is called a 4x4 Hadamard matrix. So this form, there's a lot of different ways you can write this. The important thing is that W is orthogonal. I should have actually written that on the slide here. W is orthogonal, meaning that any 2 rows, the dot product of any 2 rows is 0, or 2 columns is 0. And this is a convenient choice. There's a number of them, but they're all related by permutations, so you could just pick one. So usually in quantum computing, people talk about the Hadamard matrix, and what they mean is a 2x2. It's 1, 1, 1, 1, and -1. This is the general form. I think Hadamard introduced it in the 1860s. These kinds of matrices, they have very nice properties, which we'll get to in a second. But just keep this W in mind here. So the property that the Hadamard matrices have, and that's the key part for actually the gauge symmetry here, is that they have what's called an automorphism property. And that makes the Hamiltonian invariant locally. The idea here is you can hit the W on the left and on the right with a matrix and get your W back. So the W here is this 1s and -1s that I showed you in the prior slide. And then the right matrix is going to be a monomial matrix. And the left matrix is also a monomial matrix, only with pluses and minuses. And when you multiply these 3 matrices together, you're going to get W back. And the important thing is that the right matrix, you can shuffle the -1s around in the diagonal as long as you have an even number of -1s in the right matrix. So just to be a little bit more formal about it, the sigmas will transform, the gauge spins are going to transform according to the right matrix. That acts on the gauge spins, and there's an even number of spin flips because there's going to be an even number of -1s in the diagonal. And in the matter spins, I'm going to allow this permutations and flips and permutations. And I can permute the matter spins because they live inside the vertex. They don't mess up the lattice structure. The gauge spins, I can only do spin flips on them. I can't permute them, right? Because then if I just go back to this picture here, I can't switch the green dots because then I'll mess up my lattice. But I can switch the states on my blue spins without messing up the lattice structure. So that's really, the ingredient that allows you to actually use this combinatorial gauge symmetry or combinatorial symmetry to construct a local invariance. Because you see, by keeping W invariant, if you look at this form of the Hamiltonian, by keeping that W term invariant, you're keeping the Hamiltonian invariant. But of course, the price is the price for that you have to pay is introducing 4 spins at the vertex.
Dmitry, may I ask you a question?
Sure.
So when you say the Hamiltonian, this H naught is the entire Hamiltonian, or there is something else?
Yeah, I'll come back to that in 1 sec. This was my next slide. Perfect question. Yep. So far, we haven't done anything quantum mechanical, I think is what you're alluding to, right? Because you have the sigma z, that's just pluses and minus ones, just a classical Hamiltonian in effect. But what you can do, I mean, if you look at the full Hamiltonian, I'm just writing it schematically without all the indices. I have this W term, which is the Z coupling between the gauge and matter spins. And then, of course, if you're looking at an annealer type of architecture or transverse field Ising model type of system in general, you can put a transverse field on. And this could be a uniform field applied to all of the spins. That term is also invariant under combinatorial gauge symmetry, okay? And that's going to be invariant because you could, permuting the mu's, that doesn't change anything because you're applying the same transverse field to the mu's. And -1 and 1 applied to sigmas, that flipping a spin is just like rotating a spin around the x-axis. You can picture that, right? Spin up goes to spin down, sigma z plus to -1, just like rotating by 180 degrees around the x-axis. So the transverse field term is invariant also under this combinatorial gauge symmetry. So what you've really done here now is you have a fully quantum mechanical Hamiltonian where you have a local symmetry in all regimes. In other words, for all values of J and the transverse field gamma. And it's non-perturbative. And in fact, the energy gap is actually 0. This thing will have several different phases. When you're in the topological phase, the energy gap is greater than 0. Okay. So that's really, just to recap very quickly, we've introduced this Hadamard symmetry, or this Hadamard coupling between the spins. We've introduced more spins, so we have to pay that price. But we couple them in such a way as to have this kind of local symmetry at each star. That's the key. And what allows you to have that symmetry is that you can permute. If you look at the left matrix, you can permute the matter spins that are at the center of the star. And it's exact, okay? So at least theoretically, that's the system. It turns out, if you actually go through, to get even more practical, then the next question is, well, how big is your gap, et cetera, et cetera. It turns out that the gap is very small in this particular case, although it's finite, but it's very small, very hard for current levels of temperature and couplings and so forth. So, which motivated us to ask a broader question. And the broader question is, let's get away from the spins and let's talk about superconducting circuits more generally. So now we introduce a different architecture, but similar in the sense that we're still going to have these Hadamard matrices. So let's think about, we're calling this thing, for want of a better word, a waffle. So now what you have is 4 superconducting wires perpendicular to 4 other superconducting wires horizontally. And they're coupled with Josephson junctions. The black Josephson junctions will have a sign of plus, and the white Josephson junctions will have a sign of minus. So it really looks.
Can I ask you another question? Sorry to interrupt.
Sure.
So when you mentioned that there is a gapped topological order, so does it mean that you actually have some excitations, much like in Toric code? I mean, what is the essence of this topological phase?
Yeah, that's right. It's a Z2 lattice gauge theory, which, and the Toric code is a special case of the Z2 lattice gauge theory. So it's that same phase.
I see.
Yeah, the Toric code is actually, it's an exactly solvable version. You can think of it as an exactly solvable version of the Z2 lattice gauge theory back from the, what Wegener and Kogut et al. Worked on. It's a, you can think of it that way, maybe in simple terms. And so that's the same kind of phase. And it's exactly the same phase that happens in the spin systems here.
May I ask a question as well? This is Mohammed. Before going to the implementation, the bottom line is that your Hamiltonian would be just in sigma z plus some transverse field.
Yeah.
So isn't it kind of surprising that
yes,
this would lead to the same phase as the Toric code?
Yes. Yeah, no, that's right. That's why we're excited about this approach. Is we weren't, you have a very simple, it's in the class of transverse field Ising models, right? You have a ZZ interaction. And in fact, you don't even have to put a different transverse field on the different spins. This gamma is just a uniform field, just like in, for example, D wave, right? And that's really the key observation here. And in a lot of ways, that was the motivation. And at least the mathematical discipline that we tried to impose on ourselves when we were thinking about this is, can we get a topological state with just these types of Hamiltonians, right? And there's a lot of, you can imagine a lot of different combinations. You have to search. We searched a phase, for want of a better word, a phase space of possible interactions. You can have a lot of different geometries of putting 3 spins in the vertex, or 5 or 6, or have a 3D structure, or have different forms of this interaction W. There's a lot of different permutations you can think of. And what it boils down to is that you have to think about this, a monomial symmetry that you're allowed to have, these permutations and rotations coupled together into a monomial, coupled with this kind of Hadamard, really this equation encapsulates the whole thing. Now you have this Hadamard automorphism, because the key here is that you have your transformations on the spins are all monomials. You see, the left matrix is a monomial. It involves permutations, but you're allowed to permute the matter spins that are in the middle of the lattice. So yes, I think it is surprising, and I think it's I think there's actually a lot of possibilities, because it's a fairly general principle that you can apply to not just spins, as we discovered as we were trying to push into something different to have a different kind of gap structure.
Yes. Dmitry, can I ask, can I think about integrating out the gauge field and get effective interactions between the matter, or vice versa, and that kind of get higher order interaction?
Yes, it's an excellent question. So looks like we're moving along nicely here. So I'm just going to jump to an appendix slide here real quick and just show you what happens, because it's actually kind of cute. And what was kind of the aha moment in a way is early on as we were looking through all of these combinations. So what you can do is the following. So just to come back to the system, you write your full Hamiltonian, and then imagine that you integrate out the matter spins here. So imagine that you have your gauge spin sigmas are in a field of mu's, if you will. So you can integrate out the mu's, and what you'll get is exactly sigma 1, sigma 2, sigma 3, sigma 4 interaction, a 4-spin interaction. And it's because they're binary variables. Okay, you can think of it as you have this the linear combination of the sigmas is like in a field of mu's, bz mu z and bx mu x, or rather let me put it the other way around. The mu z and mu x are in a field of sigmas. That's a better way of looking at it. Sorry. So this is just a single spin. You see, the mu's don't talk to anybody else. They're only sitting at the vertex. So you really just have a single spin problem here. You just have to diagonalize mu z and mu x. at each site. And they're in a field of sigmas. And that's basically what it boils down to. So I don't want to spend too much time on this, but it's not a complicated exercise. It's in the PRL paper, worked out in detail, but you get exactly the star term of with no corrections. Does that sort of answer your question?
Yeah. Yes, thank you.
Okay, so now to come back to this waffle. So let's think about other systems that you can use. Okay, it's not just spins that you can use permutation, combinatorial gauge symmetry for. You can use it for the fields in a superconductor, for the superconducting order parameters. So here we have four sets of wires that are perpendicular, two sets of wires, sorry, four perpendicular vertically and four horizontally. Okay, so you're going to have 8 phases here. We're going to call the matter wires phis and the gauge wires theta. And I'm going to write the Hamiltonian here in terms of these phis and thetas. And you'll see the same Hadamard matrix 4 by 4. W is here, that's W and I. But now, if you remember from the Josephson junction slide, the interaction energy or Hamiltonian for any 2 wires when they come together is the cosine of the phase difference between them. So you get this cosine of phi n minus theta I term. So that's your Hamiltonian in the phases. And then the quantum fluctuations, of course, in superconductors, you also have the charge, which is its complementary variable. And that measures the number of Cooper pairs on each wire. And that's proportional to the charge squared. And these C's are the capacitance. So for infinite capacitance, that capacitance term vanishes and you just get a model with just phis and thetas. Infinite capacitance means that the Cooper pairs, you can have as many as you want on each wire. They're all just, it's like a fluid characterized by just a phase. In the other limit, the phases are not good quantum numbers, and it's the charges that are good quantum numbers. But let's start with the classical limit first, with just the phases. So, but before we do that, let me just show you how to build the lattice. So now, this is the original slide that I was showing you. I'm going to connect these waffles to each other in this kind of square lattice interaction that you see blown up there. So the thetas. So you'll see that each waffle next to, 2 waffles next to each other, they just share one gauge wire, one theta wire. So if you stare at this for just a couple seconds, notice also that the gauge wires don't extend throughout the system, right? You just have waffles, they share one wire and that's it. So, and they're all of uniform length, so it makes think about all the capacitances is the same for the time being, although technically they don't have to be. So this is going to be our waffle that we use to build a lattice. And the combinatorial gauge symmetry, I'm not going to go through the details, but the commutators that you have to preserve here, just like in the spin system, we have to preserve the Pauli spin algebra of SU2. Here we have to preserve the commutation relations of the phases and the charges, which I dropped all the indices here, but on each waffle, of course, you have 4 phis, 4 thetas, and then 4 charges on each wire. And the canonical commutation relations are here that you need to preserve. So an interesting thing happens, because remember, we were talking about all these loops with the spin systems. So now what happens here, if you look at the right side of this page, I'm going to take this limit where the gauge capacitance is very large. So my theta is I can characterize my system by the phase of the gauge wires. And I could just look at this Hamiltonian with classical wires. And I just have this kind of mathematical problem of minimizing the Hamiltonian as a function of phi and theta. And it's an interesting problem. And it has an interesting solution. It turns out that the minima, I'm not showing what the solutions are for phi in the picture. I'm just showing you the solutions for theta. What you'll find is that out of each waffle, you have to have 2 thetas that are the same, alpha alpha and beta beta. Okay, and that's the blue, and that's the analog of the spins where I have the blue and the red. Remember, I have to have an even number of -1s and +1s. Here, I have to have two thetas that are alpha and 2 thetas that are equal to beta. Now, beta can equal alpha, but in general, theta can have any of these values. Then the other solution is that I can kick any of these 2 thetas by pi, or rather, I can kick 4 thetas around a square of these waffles by pi, and I'm still going to get a minimum. And that's this kind of rainbow plaquette that I'm showing on the right. And mathematically, if you look, sorry, I can't point to this thing, but you've got theta equals alpha beta or alpha beta. So 2 of the thetas around each, coming out of each waffle have to be the same. And what it leads to is a very nice picture in terms of loop models. So if you look on the left, don't look on the right for a second. If you look on the left, you look at each waffle, think about it as a star. And out of each waffle, remember, you have to have 2 angles that are the same, 2 thetas that are the same. So I've drawn loops here that fill the lattice. And if you look at each waffle, you're going to have 2 thetas that are always the same. Like, for example, look at P beta. That's the path where the theta is equal to beta all the way around it. So if you follow the blue line, you'll have 2 legs coming out of each waffle. Then let's say you look at P alpha, which is the red one. Again, you have 2 legs coming. I've imposed periodic boundary conditions here. So again, you have this kind of lattice situation where all the waffles are happy as long as you have these 2 angles are the same out of each waffle. And that is a loop model. And you can have the same phase on each link. And it turns out it can only be modulo pi because of this kind of minimum solution that I showed you, where you can kick the thetas by pi all around a plaquette. On the left, you can, the other thing to point out here is that these loops intersect. There's all this literature about ON models, where sometimes the loops are allowed to intersect, sometimes they're not. There's all these different flavors and different lattices. This turns out to be one of those loops. And the fact that you have also this pi symmetry, this is actually the Z2 loops, because what I can do is I can superimpose on the loop model on the left. I can just superimpose any kind of loop structure where I add pi to any of the angles around the loop, and I still get another solution. Okay. So that's the Z2 structure, and we're just talking about the classical models here. That's what's beautiful about it, is you just look at this Hamiltonian with thetas and phis, and it's a purely classical model here. We're just looking for its minima, but the thing that connects them is this geography or geometry with the Hadamard matrix W. Okay, so now let's get into the physics. What happens in reality, or what would happen when you start talking about thermodynamics? If you start talking about the free energy and what's going to minimize the states, you have to maximize the entropy, of course. That's going to compete. And for the loops on the left, what's favored is a loop. We're calling this a loop crystal. So if you have these small loops, because there's a lot of ways to fill a plane with these small loops, as long as you just have the same color all the way around the little plaquette, around the little square. So you see P1, P2, P3, P4, and so forth are the smallest kind of loops that you can draw. And each loop can have any angle modulo pi, right? So P1, for example, can be characterized, that light blue can be characterized by any alpha, any angle alpha between 0 and pi. So that turns out to have the highest entropic contribution to the ground state. And this also means that the U1 loops are not going to order. If you look at this crystal structure, you see I can vary the angle around in P1 independently of P2 or P3 or P4. right? So you have
But
this.
is it some sort of fine-tuned point, or it's stable against some small perturbations? So
I'm gonna get to that. That's a perfect question. Thank you. I will get to that. It is a special point, but it has a region of stability around it. So I'm going to get to that in a second. So this is kind of the crystal loop phase, and then you still have those Z2 loops on top of it. So I can go around and still kick the phases by pi around any path in the lattice. And mathematically, I'm not going to get too hung up on this, but I just want to point out that what happens here mathematically is that at zero temperature, the partition function factorizes into this crystal loops and the Z2 loops. And in the language of loop models, you can write this crystalline loop in terms of these loop fugacity, where the fugacity lambda goes to infinity. So it's like an O infinity model. So now so this is still a classical model, okay? So now of course we have we're interested in quantum. So we're gonna add quantum fluctuations. I'm gonna get to this critical point here. Well, technically it's not a critical point, it's a special point. So I'm gonna work at zero temperature still, and I'm gonna add capacitance to it. So the classical model could be thought of as having infinite capacitance. So my 0 point here is at infinite capacitance. And now I'm going to start dialing the capacitance down, going up in the axis. And that will add the quantum fluctuations to it. And then at the same time, you can think about deviations from the Hadamard matrix, from the Hadamard point. And this is where kind of the tuning comes in. I can think about deforming the Hadamard interaction. If we have time, I'll show you the details in the appendix. And what happens in that case is, let's say you're not deforming the Hadamard matrix. You're still sitting at that special ones and negative ones interaction, and you just start going up in the axis of adding quantum fluctuations. As you decrease your capacitance, eventually you're just going to be in a disordered state, the yellow. But on the way there, you're going to cross through a quantum spin liquid, which has the Z2 topological order, the same kind of order as the Toric code or the Z2 gauge theory. That's the kind of red or pink area. And then, but at some point, if you're deforming the Hadamard matrix, you're going to get into an XY ordering, which is more like the usual XY ordering phase. So that pink area is where you want to be. So you can deform. So you can see if you're at some sort of quantum fluctuation level in the red area or pink area, you can deform the Hadamard up to some point, at which and then the more conventional ordering takes place.
So and how do you know this is actually the phase diagram?
So so let me just, this is actually the last slide.
Mm-hmm.
So
okay.
And then I'll come back to some, so I got 2 more slides and I'll come back to that, okay?
Great.
Okay, so now the extreme quantum limit, I want to put, we're calling this the WXY model by analogy to XY, and we have this W Hadamard. In the extreme quantum limit, basically your 5 variables, they become kind of raising and lowering, or operators in spin space. It actually, this thing actually becomes, we can get to the details if we have time. It becomes an XX kind of XY model, which is mu X sigma X plus mu Y sigma Y, except it's coupled with this W matrix. And that's in the extreme limit where the both capacitances are small on both the matter and the gauge wires. And in that limit, the geometry is really the same thing. You have this waffle is the same thing as this toric code lattice that I showed you, except the interaction now is not sigma X mu X, but it's not sigma Z mu Z, it's now XX and YY. So the quantum fluctuations are here from the start. And this is where we get into the conjecture area of the PRL, where our conjecture is that there's only one energy scale here, which is J, and we have quantum fluctuations because from XX and YY, they don't commute from the very start. And so the conjecture is that we'll get a quantum spin liquid here with a gap of order J, because that's the only energy scale. So just to conclude, two key points that I would like to convey here. One is that combinatorial gauge symmetry is the general principle, because it preserves the commutation relations for spins, bosons, fermions, phases. We really focused on spins and phases here. And it will give you exact topological states. It's not perturbative, right? These are, we're Hamiltonians here with the full gauge symmetry in the full phase space. And the systems that we've described here, we were able to utilize the combinatorial gauge symmetry to construct spin systems and superconducting circuits just out of two-body interactions, right? To give you Z2 topological order. So that's that wraps up the body of the talk. And before I take any more questions, maybe I'll come back to Victor's question about the deformations, or how do we the phase diagram, correct?
Yeah, I mean, maybe we should just open. Well, thank you, I guess, for the talk. You know, I don't know what the usual procedure here is. Danny, you should tell me if people are. You're the organizer.
Yeah, so we usually just open it up to questions at this point.
Yeah, so thank you very much. You know, normally we upload the speakers, so thank you. This is great and perfect timing. So I think, yeah, there is time for questions. So it doesn't have to be my question first, so maybe some other people should also have the opportunity to ask.
So I have a question, Dmitry. This is Shankar.
Shankar, yeah.
So I agree that just purely on dimensional ground, the gap should be of order J. It's a very reasonable speculation. But we also know from other examples of spin liquids that in nature, that doesn't seem to happen. Meaning, yeah, it's of order J, but there could be a pi to the power 10 or something in the denominator. I mean, most of the spin liquids almost never order, as you know, and it's kind of a mystery. So is it possible to do some numerical work or something to see what the gap actually is? Or did you do anything like that?
Well, yeah, so we've got a number of projects, a couple of projects along in those directions. Yes, we're looking at that. We haven't found an analytical approach yet to that particular conjecture, but there are things we are working on to get at it numerically. We have a couple of other things just from the practical point of view of trying to implement it in various, in real life, or at least parts of this. I know that's not exactly what you asked, but there's a number of things you can look at here, including the numerics of the gap.
The reason I'm asking this is actually to think how you can induce experimentalists to try this. You know, I have been, as you know, working on it for 20 years. And the problem one faces always with any topological system one comes up with, whether it's a specific topological system or a circuit like what you're talking about, is in the end, the gap turns out to be small for experiment. This was the problem where, you know, Microsoft eventually gave up on 5-hop, although I convinced them originally to use 5-hop as the qubit. And I think they should still do it, you know, because it's such a beautiful, interesting system. In the end, because the gap was very small. When the gap is only 100 millikelvin, experiments are difficult and the protection is determined by the gap. We are facing similar problem in this Majorana nanowire, where the gap is not 100 millikelvin, it's 0. So, you know, in the end, if you want to persuade any experimentalist, you have to tell them what the gap is in actual Kelvin, you know. So this is the context of my question.
Yeah, and I completely appreciate that, and that's exactly, you know, why it was. It's a very important observation, and probably the key observation to actually building this thing, and so that's why I was pointing out that our motivation actually in moving on from this particular Hamiltonian here, the transverse field Ising model, is that the gap was too small, right?
Yep.
And so what we're looking for here is a gap that's bigger, and why we're speculating here that, or conjecturing that the gap is of order J. Now then the question is it J divided by a million, right?
Yeah,
Or is
exactly.
it J
This is exactly my question. Right?
And that's, I think it's an important question. We think it's, more like J divided by 2, right? But again, it's, we're working on that.
Right, like, in your thesis system, the beautiful work, the same argument will say that the fractional quantum Hall gap at 5½ is E square over Landau length, but the actual gap is much less, right? I mean, that's like the J there. And, it's these numerical calculations are well defined. They're not easy, obviously. You need a large computer, but they can be done. And if you can induce somebody to do it, I think experimentalists will try this model. I mean, it's a very, very doable model in the lab. Anyway, I will let others ask questions now.
So actually, I think there is an experimentalist in the audience. I saw Vlad. I don't know if he's still around. Maybe he can comment. Maybe not. Okay. I was just trying to get experimental.
So I had a question, if that's okay. This is Danny. So it looked like in defining the combinatorial gauge symmetry, you had these L and R matrices, and it looked like there were quite a few choices for those. And so I guess, do you have larger than a Z2 on-site symmetry in the original model? Like, do you have many different choices of these L and R matrices? And if so, what is the relationship between the full symmetry group of this little interaction and the Z2 gauge symmetry that you get out in the effective model?
Well, so a couple of things. So the Hadamard matrix, you're right that this 4×4, there's actually a whole theory of these matrices, and I forget what the exact number, I think it's like 192 or something. If your constraint is the following, that you can only have +1 or -1, and the matrix has to be orthogonal, then there is a well-defined set of Hadamard matrices that you can have. The first Hadamard matrix is 2, and then it's 4, and then multiples of 4. So then I think it's 8, 16, and so forth. And there's a whole theory of them, which ones are related by isomorphism. In 4×4, there's actually one unique one. So the rest are related by isomorphism, so you could just pick one here. As far as other geometries and more generalized Hadamard matrices, I don't want to speak prematurely, but there are other things you can cook up. But here in this particular model, you have to. So if you're going to have this kind of automorphism and monomial symmetries, you're really pretty constrained. It has to be 2×2, which then you're just going to end up with a 1D system. You can have a 4×4. Maybe you can cook up something that's more complicated, 8, but then you'll have to be constrained by the lattice geometry. Then you'll have to have a vertex with 8. So that doesn't work, right? Because you can't draw a lattice with 8 legs. So really, 4×4 is the natural one when you're constrained to have +1s and -1s.
I guess the question I had is, how much freedom do you have in the L and R's in the gauge symmetry transformation here? Are these aren't just the unique L and R matrices that preserve W, right?
Yeah, that's right. So the first observation is, if you fix the R matrix, the L is determined by this equation, right? Right. So if you fix the R, you can then solve for L. And what you can have on the R matrices, it turns out, if you require that L is monomial and R is monomial, and R also has to be diagonal because you can't screw up the lattice, then the R can only have an even number of -1s. And that's exactly, if you try a different R with, let's say, 1 -1, you're not going to get a monomial L.
Right, so the symmetry group that you have here is like Z2, is multiple copies of Z2, right? One for each different choice of R. Is that right?
No, because R, if you try, let's say you try independently, let's say you do, you have a -1 in the top left-hand corner of R, and then you have the rest are +1s. If you try that,
Right.
L is not a monomial.
Right, but there's multiple choices of 2 minus 1s, right? You could have the first and second entries, or the first and the third entries, and all of these things. And any product of those two matrices is also gives you some automorphism. And so it looks like your symmetry group is actually larger than Z2.
No, it's exactly your Z2 group, because, well, it's not Z2. It's not as in 1, negative. It's not like the 2 elements of 1 and negative 1. It's exactly your symmetry group of the 4-body interaction, right? So you just want the symmetry of, let me see where I have this slide. The thing where I put the sigma 1, sigma 2, here we go.
Oh, I see.
You see, you just want the symmetry of that star. I mean, it's called Z2 gauge theory, but
right. I see.
That's the origin of the underlying spins, but you really want all the symmetry operations that preserve this product of 4 spins.
Okay, thank you.
Or Danny, on the lattice, you actually have the Z2 in this language, the gauge transformation is associated with the plaquette. So that Z2 is basically when you flip 4 legs on the plaquette. So you end up flipping 2 at each vertex. And that's the Z2 in the local Z2 gauge theory. It's not associated with the same term. Yeah.
I see. Great. Thank you.
Yeah. So what Zicheng is saying is that, you see, there's a picture that we had in that PRL that you can create these kind of loops on the lattice. You see, because you start out with your underlying lattice where you have these 4 spins on the sides and 4 spins on the lattice, and then you flip 2 of the legs. You're applying the R matrix on the orange legs, right? So the fact that you have 2 negative 1s in the R means you could draw these legs on these loops on the lattice as well, just like in the Toric code. Except every time you do that, you also have to flip a bunch of mu's in the middle, if that makes sense. So your plaquette operator is kind of a dress plaquette operator, which I've drawn here. So the flipping of R's corresponds to applying sigma x on the legs, and then you have a left matrix that corresponds to permuting and flipping a bunch of matter spins on the vertices. So your plaquette operator is just a little bit more complicated, but it's the same concept.
I see. Thank you.
Can I ask an experimental question? This is Vlad. I do experiments with Josephs and junctions. So I find that this waffle is a rather simple device to work with, but I'm concerned about one effect that is maybe missing from your model. So when these thin wires are very small and have large charging energy, they become sensitive to external electric fields. Essentially, there's this concept of offset charge that you need to offset every little q and big q in your Hamiltonian by some constant which has the meaning of the local electric field. And usually these things are completely random. They're due to some dirt in the oxide around these devices. And it's a generic property of pretty much any model of superconducting grains with small capacitance connected to each other. So I'm curious how robust the phases that you describe are to this random offset. Thank you.
Yeah, no, it's a good question. We did not consider that particular perturbation, right? We considered other deformations of the interaction, but that's something to look at.
Yeah, that these offset charges, they sort of have a history of screwing up various interesting models, just because, you know, it's just something that's always there. It's completely random, can be controlled. I think that there's a variant of it is where the offset charges just fluctuates by E, which is the parity issue, where just quasi-particles appear and disappear. That thing, I think, is causing problems to Majoranas. But in general, the offset charge could be just a continuous random variable. So that's probably an interesting perturbation to consider. Thank you.
May I ask a question? Oh, okay.
Sure. Yeah, probably
sorry,
introduce yourself though, because it's hard to see who is talking.
oh, okay. I can go start the video. I'm Ali. I'm a graduate student at CMTC. So I had two questions. First, you said one of the nice features of this model is that it like gives you topological phase with just two-body interactions. How does it compare with the p-type honeycomb model? Because that's also, I think, two-body interaction, and the gapped phase is like in the same topological like class phase as the Toric code. So how does it two compare?
Yes. So yes, and I was referring to the type honeycomb model here. It's a different phase, right? What we were trying to do here is find a way to build something that only used available interactions, and it's been hard to realize this type honeycomb because of you need these kind of anisotropic interaction. You need like XX on one leg, YY on the other, ZZ on the other. It's been hard to get that kind of interaction. So
this
but
one
you're right,
is just
that's the only two-body example that I know. There is two-body example, it's just hard to build.
There is also like this Wolf-Schrieffer type of perturbation type of like models that, I mean, the Hamiltonian is two-body, but when the effective Hamiltonian is like many-body. Like there is this like type of topological models that are built from two-body, but as you said, your model is non-perturbative. So I think
that's the distinction. Yes, that's true, and there are those kinds of models. You have to go to some sort of limit and get an effective Hamiltonian here. Here are symmetries built in, you know, in the whole phase space, right?
Right. Just another question. Have you thought about like generalizing this to like 4D and getting like 4D Toric code, which has this like nice properties of like self-correcting, like the excitations are kind of like not
we do have some results for the 3D Toric code and a fracton model also, the 3D in the PRL.
Oh, I see.
Yeah, so you can do that. I mean, I'll give you a flavor of it. Like you can, you know, for example, for fractons, you have three planes. You go to 3D, and then you have three intersecting planes, and you can do this kind of, you can introduce these matter spins in each plane effectively.
I see.
So you can generalize it to higher dimensions.
Cool. Thank you.
So any other questions? So maybe I'll ask, presumably last question, so kind of returning to the phase diagram you showed. So I was just wondering, is it a result or a conjecture?
No,
the one with this pink region, which is supposedly a stable spin liquid.
Yeah, no, we did work through it. And there's, I didn't want to get too deep into it. It's definitely, it's in the, it's in one of the sections in this, on the archive right now, which we just posted in June. But essentially, when you look at the Lagrangian of this thing, you have this capacitance term, which is the fluctuation of the theta variable. And then the way we perturb, you have to pick a way to perturb the Hadamard. And this is the one example we have is in the paper is done this way, where instead of -1, you put in phases down on the diagonal. And then what happens is you get three kind of terms in your Lagrangian. You have this perturbed interaction, which we call J eta. Eta is the parameter here. And you really have three terms in the Lagrangian, which is this kind of the original piece that's unperturbed, and then the perturbed piece. And, you know, it turns out that these different variables are actually, it's similar to the models that Sajdev wrote about in his other work recently in 2018, where you can map these kinds of, or draw an analogy to these kind of phases where he has 4-body and 2-body interactions. So it's relatable to that. I don't know if it's the scope here is to get too deep into it, but there's we did work through the phase diagram. It's not conjecture.
Okay. So if there are no more questions, I think we should thank Dmitry for this fantastic presentation and very interesting work. So yeah, thank you very much.
All right, thanks everyone.
Yeah, thank you.